and everything. Yeah, and everything I'll be discussing today is joint work with Vishesh Jain, Will Perkins, Ashwin Sah, and myself. So the main goal of this lecture is to establish a local central limit theorem for the hardcore model and use this to sample efficiently independent sets of a fixed size. So just for a concrete list, let me define the hardcore model on a graph. So this is the hardcore model with fugacity lambda or parameter lambda. So fix a graph G. And you let the partition function at lambda be the sum over sets, which are subsets of the vertex set, which are independent sets. So by an independent set, I just mean a set of vertices such that no two of them have an edge between them. And you look at lambda to the size of S. And in the hardcore model, you sample S proportional to lambda to the S. So sample S with probability lambda to the S over ZG of lambda. So when lambda equals 1, this is sampling a uniformly random independent set. As lambda increases, you're sort of favoring larger independent sets. For small lambda, you're favoring smaller independent sets. So this model has been extensively studied, and the setting we'll be considering is the case where G is a bounded degree graph. So let's say a 3 or 4 regular graph. And here it turns out the really interesting connections come when you sort of connect a probabilistic perspective with sort of a computational perspective. So this is a sequence of works due to Weitz, Sly, Sun, Galanis, Stepkanovich, and Vigoda. And these results together give a very precise understanding of sampling from the hardcore model. So let G be an n vertex max degree delta graph and let lambda critical be some really funny value, which right now it's not going to have much meaning, but you can just, for now, just take it as some fixed value based on delta. So first one, if lambda is less than this critical value, so in particular, you're some fixed bounded amount away from this critical value, then there is a n over epsilon. So there's some polynomial time algorithm to estimate ZG lambda to within 1 plus or minus epsilon. So below some fixed value, you can estimate it exactly. But if lambda is bigger than this value, so this again, this funny critical value, unless NP equals RP, you should basically think of this as P equals NP, something slightly different. Then there does not exist. And FP Ross. So an FP Ross just means that in polynomial time, you can get your value to within a 1 plus or minus epsilon approximation to approximate ZG lambda. So this is a really beautiful like phase transition result because it's telling you exactly where the transition between where you can approximate and where you can't. RP is randomized polynomial time. So there is a precise point at which you can, the task is computationally feasible, and below it, it's not. But sort of the natural question, given this result is, or when you see this result for the first time, is what is this magical value coming in? Where is this magical value coming from? Like, what is the probabilistic meaning of it? It turns out there's a very nice explanation. So the reason for this magical value is consider some vertex V and then degree delta minus 1. And you consider a tree of height T. Okay. And now, so it's a tree of height T, and then I specify on the boundary which set of vertices are included in my independent sets. Some of them are not, some of them are, and I tell you I sort of tell you the bottom of the tree. What do you know about the top? So you should think of the height T as tending to infinity. And the key point is if lambda is less than this critical value on the tree, so this is just some explicit recurrence that you can check. It's not very easy, but you can check this directly. So the probability that B is included in the independence, included in the independence that you sampled, say, conditional on the boundary. So the boundary here is the bottom of the tree. As T tends to infinity, this tends to some fixed value. But if lambda is bigger than lambda critical, then this probability does not actually necessarily tend to a limit, does not tend to a fixed limit. So what this is saying is that below this critical value, you sort of have correlation decay. So, I mean, this is essentially the property of having correlation. I'm being a little bit imprecise, but if you know everything at the boundary, then you don't know any information about the top vertex. If you're below the critical value, but above it, you do. So in some sense, this is giving you a connection between being having correlation decay and being algorithmically tractable. It turns out, however, that people have actually understood this. So this is not the only connection you can actually establish at this critical point. Turns out something.
Excuse me, can I ask a question?
Sure.
So the delta is, you say it's the maximum degree, yes?
Yes.
So that's possible. Just say one vertex has delta edges, but all the others are kind of arbitrary as long as it's less than or equal to delta. So
Sure.
then I'm wondering then that the delta is kind of could be a very local behavior, but ZG is for the whole graph. How come the delta plays such an important role?
So when I say this results for NP equals RP, I'm saying there exists a like if you were able to do this on all graphs of max discrete delta, then you would violate some computational assumption. It's not that all graphs with max degree delta are the worst possible. You can try to get a more precise graph by graph understanding, but it turns out that most of the literature sort of really focuses on using the max degree as the key parameter.
Okay.
And this is natural in the context, basically because of this this tree example. That's sort of where sort of understanding the max degree assumption comes in.
Okay, thank you.
So you can also then use this. We can also now just study the partition function sort of at this region of criticality. And one thing that turns out to be very useful to understand is what are the roots of this partition function. So ZG of lambda is some polynomial. What are its roots? So for lambda and the complex numbers, we attempt to evaluate ZG of lambda. And the remarkable thing is, if you have a max degree assumption, then you get a zero free region. So we have that ZG of lambda is not equal to 0 if lambda is in following region. So as before, G is a graph of max degree delta. So I'm not going to write this anymore. So you have 0, and then you have a lambda, this critical value on the real line, and I'm going to give myself some delta of root. Then there exists a tubular region of width f of delta, such that there are no real zeros. So if you sort of give yourself a little bit of room from the critical value, there exists a strip. And this strip is independent of, like how wide the strip is independent of the number of, let's say, vertices in the graph. It's just some fixed number based on delta, like capital delta and little delta. And this is an inherently interesting result, but one of the real motivations to understand this, it might seem unmotivated at first, but from an algorithmic perspective, this actually turns out to be critical. So using ideas due to Baravotic and Patel and Rex. So using this zero free region. And Taylor expansion. Allows one to deterministically approximate. CG of lambda. So this lets you recover this result regarding the deterministic regime, regarding getting a deterministic approximation of the partition function. So this sort of gives another one of these, one of the really nice properties of this model. So somehow the threshold for correlation decay is the same as the threshold for algorithms are being algorithmically tractable. It's the same as same as the point at which you can establish a zero-free region for the partition function. And there's even more here. Recently, you can even show mixing of Glauber dynamics. So let's say you want to sample an independent set from the hardcore model. There's a natural Markov chain on this. What you do is you fix some independent set, you then pick a random vertex and you locally resample that vertex based on everything else in the graph. Because of the structure of the partition function, there's an easy way to do this. So this is a very natural, Glauber dynamics is a natural way to sample an independent set. So there's mixing of Glauber dynamics in O lambda of n log n time. For lambda less than lambda critical. So there are a bunch of these results that are sort of coming in at the exact same time. Sorry, this is a recent result due to Inari and girl. So I've discussed sort of at this point pretty extensively this model regarding the hardcore model. But at the beginning of the talk, I promised you that we were going to understand sampling independent sets of a fixed size. And the purpose of this talk is sort of to connect these two models in a way that allows you to sample an independent set of a given fixed size. So it turns out I will need an upper bound on the size of the independent set I can sample. So this is another magic number, just coming from the critical value of the hardcore model. So this is just some fixed number. So our main theorem is actually regarding the hardcore model, and then I'll discuss its applications. So you fix so delta as before to be bigger than 3, and epsilon greater than 0, and let lambda be in this critical regime. So I need to be slightly less than this new magic parameter. So given a max degree delta, G, draw an independent set. I from the hardcore model at fugacity lambda. Now, since I have to write down a local central limit theorem, I need to define mu, which is the expected value of the size of the independent set, and the variance, and the normal density function. Then you have exactly what I said. You have a local central limit there. So every point in the distribution has exactly the size you would expect. So okay, so I just wrote a little O here. This can be made quantitative. I'm going to ignore that for now. Why is this the prediction you expect? So I want to understand the amount of probability at some point t. So the mean is mu, the variance is sigma. This is the number. So t minus mu over sigma is the number of standard deviations your way. And since I'm only looking at how much mass is on that particular integer, I sort of put an interval of length 1 down and I integrate the Gaussian. This is roughly what you get, and this sort of naive prediction is actually true. So not only do you have a central limit theorem, but you have a pointwise guarantee with a local central limit theorem. So this is a purely probabilistic statement, but why is this useful? Oh, sorry. This is actually the same critical value, but so why is this useful? So the proof, the proof will be a Fourier analytic in nature, and the proof essentially immediately gives a deterministic algorithm. For counting independent sets. So it's not up to lambda critical, but it's some other parameter, which I wrote here. You have to open up the proof a bit, but this is essentially immediate, and you can't do any better than this. So this is improving on an earlier work of Davies and Perkins, who gave an O tilde n squared randomized algorithm. So instead of a deterministic algorithm, they are a randomized algorithm, but they wanted they asked for an F beta. So furthermore, given this result, you can sort of this also gives a simpler FPROS. And this is really based on the proof. This is not black box from the result. So black box from the result, you can give a very simple order n to the 3/2 time algorithm. But if you sort of look at the proof very carefully, this gives an O tilde n to sample an independent set of a given size. And I don't know if I've said this, but O tilde just means hiding log factors. So this gives an essentially optimal algorithm for sampling an independent set of a fixed size. So in the remainder of my time, what I'm going to do is sort of sketch the proof of this result and sort of hint at how you make it algorithmic.
Excuse me, I missed it. What's that? The probability is x or chi equal to t? I missed that part in the theorem, in the statement. Yeah.
Oh, so x is oh, sorry. The size of the independence that you sample satisfies the local central limit there. Sorry about that. I don't know where that error happened.
Okay.
Yeah. Is it clear now?
Yeah. Thanks.
Okay. So the first part of the proof. So I mentioned a bunch of these results. I'm actually going to just start to use them at the start. So first, well, okay, if I'm going to prove a central limit theorem, I should be able to say at least something about the variance. And I'm going to bound a variance, I think, in a way I think is quite funny. So let's look at ZG of lambda. This is, you can sort of look at it as, so ZG of lambda over ZG of 1 is just the probability generating function for the random variable I. And you can write down what it is. It's sum from j equals 1 to n of 1 minus lambda over rj, where rj are the roots. Or sorry, were the roots of zg of lambda. So, okay. So getting a lower bound on the variance of I is pretty easy. I'll sketch the proof later. It's not very difficult. But the difficult part is actually establishing an upper bound. And a purely probabilistic proof of this fact is quite hard. I don't know an easy proof. But turns out there's a result I've already said that lets you do this. What you can do is, well, I have access to this, basically the probability generating function. You can do some manipulations with probability generating functions, and you can write down an expression for the variance in terms of the roots of the polynomial. So it's minus lambda times the sum from j equals 1 to n of 1 over rj, 1 minus lambda over rj squared. Sort of very crudely bounding this is bounded by n. So I'm hiding some factors in terms of lambda, max over j of 1 over 1 minus lambda over rj squared. So, so we know from earlier that we have a tubular region around around our point where we have no roots, because lambda is strictly less than lambda, the critical value. So we know there's a small region of the complex plane where there are no roots for some fixed value. So this is less than some constant. So basically, just by applying the zero-free region and rewriting the variance in terms of the roots, you can get a bound on the variance. So this is a purely probabilistic consequence of just understanding, of using the roots. So, okay, so now we've established a bound on the variance. Well, okay, if I'm going to prove a local central limit theorem, I should at least be able to tell you how to prove a central limit theorem. So this is the second step. And here we use a beautiful recent result of Michelin and Sahasrabudhe. So x is just some random variable. Let fx of z be the probability generating function. So I'm summing from x equals k. Probability of x equals k is z to the k. You have, let's say, the expectation of x equals mu, the variance of x equals sigma squared. So now, okay, so now I need to impose an upper bound on the size of x. So you should really think of x as some non-negative random variable that takes values between 0 and is integer valued, and let delta be the minimum over its roots, like how close the roots are to 1. So remarkably, I think this is a really beautiful theorem because you can turn the information about roots into a central limit theorem. So just knowing that you have no roots close to 1 sort of automatically implies you have a central limit theorem. So I'm just going to write down with even a quantitative phrase. So this is pretty remarkable. And I think initially it's not obvious what the intuition for this is, but I can give a very simple case, sort of where the intuition comes from. So the most extreme case is if your roots are all negative real numbers. So this is sort of the most extreme way of being away from one. Then if you just use that information, then you can write your generating function, your probability generating function as a product of Rix plus 1 minus Ri. Where Ri is just a small modification of what your root is for Ri in 0, 1. But notice that you can reinterpret this. This means that X in distribution is just the sum of Bernoulli random variables, Bernoulli R1 up to Bernoulli Rn. And at this point, you can apply any quantitative central limit theorem, and you'll be able to prove a central limit theorem for X. So somehow, this theorem is a more general version of this very simple observation. So now we have a central limit theorem, and well, okay, so we need to go from our central limit theorem to a local central limit theorem. But this is a pretty difficult model to get a handle of, at least operarily, because this is understanding independent sets on a fixed graph. I mean, there's not a lot of independence. So remarkably, you can actually sort of handle this in a pretty classical way. We're gonna prove a local central limit theorem through a Fourier analytic approach by sort of finding some independence. So just so that I can be consistent with the notation I've used above, so X is just going to be the random variable which denotes the size of I. And let X prime be X minus mu over sigma. So an easy computation, easy Fourier analytic computation, so tells you the following. So suppose I want to understand the probability of being at a particular point t. And I want to bound it from its naive expectation, if, let's say, it looked exactly like the Gaussian. Then you can instead turn this into a problem about controlling the Fourier coefficients of your random variable. So you can look at the Fourier coefficient at height t minus the Fourier coefficient of the Gaussian. And it suffices to prove that this is small. So there's some extra term of e to the minus pi squared sigma squared over 2. I mean, this is much less than 1 over sigma, the error we're aiming for. So it really suffices to understand this integral. So what you really want to show is you want to be able to control this integral from minus pi sigma to pi sigma of expectation of e to the it x prime minus expectation of e to the it x. Okay, so it turns out you should sort of think about this problem in 2 different regimes. So first, note that this is not really in the context of a normal central limit theorem. So instead of going to t, which is some fixed height, you're going to t, which is of height, the standard deviation. And the standard deviation in this model turns out to be something like square root of the number of vertices. So this is a height that is growing. For the central limit theorem, you only really need to understand t, which is of some fixed size. But this is saying I need to be able to understand all the way up. Okay, so it turns out you divide this into 2 ranges, and for t small, this follows from the central. This follows from the central limit theorem. But Now let's consider sort of t, which is the most extreme case. And I think this is pretty representative. So say you want to understand where t is equal to pi times sigma. Then it turns out that, well, at least for the Gaussian, e to the itx decays very fast. It decays something like, so it decays with the Fourier coefficients decay like a Gaussian PDF. So really this question is asking how small so just by triangle inequality, it suffices to understand this for t large. And when t is equal to pi times sigma, this becomes equivalent. So this just requires some computation. The expectation of -1 to the x. So I sample some independent set and I take -1 to the power of that. What this is actually saying is you want to understand, if I sample an independent set, is it equally likely to have even size or odd size? And this is sort of clearly not within the domain of a central limit theorem. And we need to be able to handle this somehow. The key idea is that you can actually, if you sort of carefully think about the model, extract some randomness. So imagine you have some graph and you have some center of the graph. So I'm just going to call this center S. And what I'm going to do is I'm going to find a set of vertices, which are all distance. I'm going to find some vertices Z1, Z2, Zn prime. So you can find a linear number of vertices. So here's where I'm using the assumption that we're in a bounded degree graph. I'm going to find some linear number of vertices, which are all separated from each other. And notice that if I give you the center, if you think about what the hardcore model does, it turns out conditional on the center, whether Z1 or Z2 or Zn is in the model is independent. And this allows you to sort of pass to a case where you have an independent, sort of pass the case where you can just understand the independent model. So in particular, let me just do the computation. So I want to understand -1 to the x, this expectation. So by triangle inequality, well, I can just condition on what happens on the inside. So if I know what happens in the center of the graph, then all the randomness that's left is in sort of these pendant vertices that are hanging outside. And let Z1 be the number of vertices that are in this cluster, Z2 be the number that are in this cluster, and so on. So then you can bound this by, or this is actually equal because of the absolute values, to the expectation of -1 to the Z1 plus Zn prime given S. There's some additive, there's some extra number in the total number of independent sets, but that's determined by S. And since I'm taking absolute values, that doesn't affect it. But now the key fact is that Z1 through Zn prime are conditionally independent. And because they're conditionally independent, well, okay, you can rewrite this as a product. And okay, so now all I need to understand is what is -1 to the zi? So zi is some like very small graph, and it turns out it's pretty easy to show that with positive probability, it has no vertices, and with positive probability, it has exactly one vertex. And because of this, this expectation is, okay, it's strictly less than 1. It's at least some fixed constant less than 1. And since I'm multiplying over n different, or order n different pendant vertices, this number turns out to be exponentially small. So in particular, this randomized algorithm, this sort of procedure lets you extract these independent bits, and this allows you to show, let's say, that the mod 2 distribution of the number of vertices in your independent set is exponentially well balanced. And if you do this for all t and then you integrate, this proves the local central limit theorem. So this is a purely probabilistic result, but our motivations were actually algorithmic. So for algorithms, so for a deterministic algorithm, it's actually quite immediate how to turn this into a deterministic algorithm. Once you realize that the correct thing to do is sort of apply a Fourier analytic approach. So for deterministic algorithm, one uses that e to the itx. Well, okay, let's write out what this means. This means that I look at e to the it to the size of x over lambda to the size of x. So x here is the independent set, and I'm summing over it over zg of lambda, because I need to normalize it to be a probability measure. And if you stare at this, this actually becomes zg of lambda e to the it over zg of lambda. So it turns out that the Fourier coefficient can be rewritten as a ratio of the partition function evaluated some complex argument and it evaluated some real argument. So using algorithms plus mentioned earlier plus the zero free region, one can approximate the Fourier coefficient for small t. And for large t, one simply uses the fact that the Fourier coefficient is very small. So this is exactly the proof I gave here. So it turns out these the zero free region and this exactly complement each other, and you can use this to get a deterministic algorithm. For randomized algorithms, this is the last thing I'm going to say. So naively, you can use rejection sampling. So if you tune lambda, so this parameter of the fugacity, so you're aiming to sample an independent set of a given size. So if you tune your parameter lambda, you can choose it so that the probability you get that an independent set of that size is 1 over square root n. So naively using rejection sampling plus mixing for Glauber dynamics, one can sample in O tilde of n to the 3 halves. But I told you that there was a way you could actually do this in nearly linear time. So the key point is, if you look at the proof carefully, the proof allows one to sample uniformly given the size of the set mod p for p approximately square root n in linear time. The key idea here is you use Glauber dynamics to sample the inside set, and you show that if you condition on your mod class, that the center doesn't change too much. So then, given this, so you can sample the center using vanilla Glauber dynamics. And the fact that this center, or if I condition on a particular residue mod p, those two distributions are close, follows from this proof. Then you just need to sample a sum of independent random variables conditioned on their mod class mod p, and that can be done in a number of ways. And so that allows you to get allows you to sample a set uniformly at random in linear time instead of n to the 3 halves. And with that, I'm done, and thank you.
All right, thanks very much. I'll clap myself. I ask other people to clap as well if you want. And I guess I'll stop the recording and I'll ask if there are any questions.